So we're going to begin lesson 5. We're going to talk about inverse operations, square roots, solving equations, and we're going to get into the GD formula sheet today as well. Starting with inverse operations. In math, each operation has an opposite operation, or what we refer to as inverse operation. And this inverse operation, what it does is it undoes the original operation to get back to the beginning of the problem. And a lot of times we call this backwards thinking. So we're going to talk about addition and subtraction. Let's look at it in an addition statement. We have 10 plus 2 is equal to 12. If I go backwards, if I go in the other direction, we call this backwards thinking. Everything goes backwards. So we use the word inversely. If I start with a 12, if I go backwards, the addition problem turns into a subtraction problem. So instead of saying 10 plus 2 is equal to 12, we can also say inversely, 12 minus 2 will take me back to the beginning, which is the 10. So 12 minus 2 is equal to 10 is also a true statement. So for every addition statement, there's also going to be a subtraction statement. Now, if I give you a subtraction statement like 25 minus 5 is equal to 20, if I go backwards, if I think backwards, what we say is 20 minus 5 equals 20. Inversely, 20 plus 5 is going to take me back to the beginning, which is going to be 25. So inversely, 20 plus 5 equals 25. So if I go backwards, the subtraction problem has to be undone by using addition to get back to the beginning. We call that backwards thinking. So every subtraction problem also can be written backwards as an addition problem. And we call these inverse operations. So each operation in math has basically what we refer to as an inverse operation. This comes in handy when we start to deal with some of the algebra topics. In algebra, we may have an equation, and we may need to find the solution to an equation. The word solution is basically the answer to an equation. An equation itself is a statement that is true. And what we need to do sometimes is we may need to find the value of the variable that makes it true. So if I want to find the solution to the equation x plus 5 equals 18, what I'm looking for is the value of the variable x that makes the statement true. And one of the cool things we can do is if we go inversely, what I can do is say 18 minus 5 is going to get me x. So 18 minus 5 would be 13, and therefore that would be the solution. So x equals 13. The 13 is called the solution. So if I look at the equation m take away 13 to get negative 20, what I'm looking for is the value of m that makes this true. And what I can do is, instead of looking at it as a subtraction problem, I can use backwards thinking, and I can say negative 12 add 13, and that should get me back to what m is. So if we use our labels of money, $20 I owe and $13 I have, we recognize that the signs are different. I have to subtract 20 minus 13. And if I do that math, we would end up with 7. And then I got to pay attention to, I'm a little bit too low there. I have to go up a little higher. So I'm just going to come over and say, well, that's going to be then a negative 7. That's going to be the value of m. Because negative 7 would be the solution to this, which means it's also the solution to this. Negative 7 take away 13 should equal negative 20. And again, remember, we can see that as terms. So negative 7 take away 13, that should equal negative 20. It should make it a true statement. And remember, we can use the circle method and just add what's in the circle. So I circle the -7. When I circle the 13, I have to include the subtraction symbol there. So it's going to be -7 plus -13. And that does equal -20, so it does check out. So that backwards thinking of going -20 plus 13 to find M was a strategy to solve this problem. So let's look at when we multiply and divide. So if I look at 3 times 5 is 15, inversely, which means to go backwards, I could say 15 divided by 5 is going to be 3. So each multiplication statement is going to have an inverse direction, which creates a division statement. So if we look at this example, 21 divided by 3, that equals 7. Inversely means to go from the other direction, which changes the division problem into a multiplication problem. So 7 times 3 gets back to the beginning, which is a 21. So it's also a true statement. So each division statement can be rewritten as a multiplication statement if you go backwards. How this may help is if I have an equation like 8 times y equals 32, if I'm looking for the solution to this, since these are connected by multiplication, inversely, you can go backwards and say, well, 32 divided by 8 must give me what y is. And 8 goes into 32 4 times, so the solution would be 4. 8 times 4 is 32. So I can see this as a multiplication problem, but inversely, I can also see it as a division problem. So if we look at the next statement, I have n divided by -4 equals -10. If I go backwards inversely, I can see this also as a multiplication problem. So -10 times -4 should get me back to what n is. And so -10 times -4, well, 10 times 4 is 40. And we know that if there's an even number of negatives, like the light switch, we know that's going to say it's a positive 40. So one negative makes a negative, but that second negative flips it back to a positive. An even number of negatives always makes an answer positive when you are multiplying. So let's look at square and square root. Square and square root, they're going to be what we call inverse operations. You knew that square means that power of 2. So 3 squared, we know that means 3 times 3, which would be 9. Inversely, we have what's called our square root symbol. So the square root symbol is that right there. That's our square root symbol. Looks like a division symbol, but it's got like a little check mark on the end there. So the square root of 9 is going to take me back to the 3. So 4 squared equals 16 because 4 times 4 is 16. Inversely, the square root of 16 basically is saying, what did you actually square to get 16? And that would be the 4. That takes me back to the beginning, which is the 4. So the square root undoes the squaring and gets me back to what I started with. 5 squared equals 25. Inversely, the square root of 25 is going to get me back to the 5. That's what it was actually squared that gave me 25. So this isn't division. You have to understand that whatever squared gives me a number, the square root is searching out for that. And that's not necessarily division. So if I have the square root of 49 equals 7, since that's square root, inversely what I can do is go backwards, go this direction, and I can say 7 squared is 49. So for each square root statement, there's going to be an inverse square statement as well. That's how you can kind of check your work, is both statements have to hold true. So the square root of 81 is going to be 9. Inversely, 9 squared has to give me 81. So if I go the other direction, the square root turns into its inverse, which is the square. So if I have square, the inverse is square root. If I have square root, the inverse is square. They kind of go backwards, back and forth there. So let's find the solutions to the following problems. The square root of x equals 10. So what this is asking you basically is, what did you square to get 10? So if I want to see this from the other direction, I could say, well, 10 squared, let's give me what x is. Gets me back to the beginning. So that means the answer would have to be 100. So the square root of 100 would be 10, and that does check out. So the square root of what is 25? In other words, 25 squared, if I go the other direction, if you square 25, that must get you back to what p is. So 25 times 25, I have to work that out. 25 times 25. So 5 times 5 is 25, carry a 2. 5 times 2 is 10, 12. Put my little 0 there, placeholder. 2 times 5 is 10, carry my 1. 2 times 2 is 4, plus 1 more is 5. So if I add that all together, that's going to be 625, 625. So that means the answer to the problem would be 625, because 625 square, the square root of 625 is going to give me 5, or the square root of 625 is going to give me 25, because 25 squared gave me 625. So if I look at this example, what squared is going to be 16? Inversely, you could say the square root of 16 must give you what x is. And what do we square to get 16 would be a 4. On this one though, 4 is not the only answer though, because if you square, negative times negative is also positive. So this actually has 2 solutions. It only gives you the positive answer. I still got to pay attention that another number squared would be a negative 4. So this example here actually has 2 solutions to the problem. So what number squared gives me 9? Well, the square root of 9 would have to give me what x is, and that would be 3. But also the answer could be a negative, because a negative times a negative is also a positive. So it actually has 2 solutions, a 3 and a negative 3. So that one takes a little bit more paying attention to on that problem. Okay, I think that concludes our inverse operations.